Hello, everyone. My name is Zapartas, and in the next few minutes, I want to present a new population synthesis tool that we have been working on in the past few years, where we use detailed stellar structure and binary evolution calculations. First, I want to say a few words about the motivation of why we would want to work on a project like this. And the main reason is because of the wealth of the observational data that are accumulated from automated surveys that probe the different outcomes of massive single and binary evolution. And this includes gravitational waves from compact object mergers, X-ray binaries and ultraluminous X-ray sources that we just heard in the previous talk, about long gamma ray bursts, short gamma ray bursts, and supernova events. And one important thing to note is that in this data, in these surveys, we do not focus on one specific system, maybe an outlier, maybe an exotic source, but we get information about the bulk of the population, about the statistical properties of these sources. Population synthesis studies have been available and kind of unavoidable tool in order to interpret all these observation. And the main idea is that we evolve a large group of single and binary models in order to predict the rate of these sources, the distribution of their properties, and the dominant evolutionary channels that lead to these events. Now, a key ingredient in this code is that we include binary systems, and this is because binarity is a key property in the evolution of massive stars, and is probably necessary for some of the sources that I discussed before. But this also means that our parameter space that we need to evolve becomes really big, because we need to take into account all the possible configuration of a binary of different masses of the two stars and the period. And this becomes computationally challenging. The way to tackle it in most of the cases up to now had been to use what we call rapid binary population synthesis. And I think the ones that I know, maybe I forgot something, but I think most of them are here. And they have been very successful in getting a lot of information. But the main thing is that in order to be rapid, they use fitting formula and lookup tables on pre-computed single stellar models of non-rotating star at thermal equilibrium at a constant mass. This makes them computationally efficient, but at the same time, it's an inherent limitation on the accuracy that we can get from this. And this affects, we lose most of the information of the inner structure of the stars in the binary system, and it affects the mass transfer, the mass transfer rate, and the estimation of the mass transfer stability, and the angular momentum between the binary components, to name a few. And here I'm showing one example of this difference, where we have the mass transfer of a star onto a compact object. And we see that the parameter space for a rapid code, the colors show the different outcome for binary black hole mergers. And we see that the parameter space changes and the outcome changes when we go from rapid codes to detailed models. I don't go to the details, but I want to show that there is some difference when we take into account more accurately the structure of the star during the mass transfer process. Apart from this, on all the wealth of data that I mentioned before, we actually have now information about the inner structure of the stars. For example, the chi effect that we see in compact object mergers give us information about the angular momentum before the collapse, as the same for long gamma ray bursts and spins of black holes in X-ray binaries. And during ULXs, ULXs probe the response of the star to extreme mass transfer loss. In order to tackle all these limitations that we had before and to have the accuracy needed, the way forward is to use detailed binary models. But the issue here now is that they are much more computationally expensive, up to even 1 million times more expensive, and they are more prone to convergence issues. So sometimes they need to manually be handheld in order to reach to a final result. For this reason, in most of the cases so far, detailed binary grids have focused on a specific part of the parameter space or in a specific evolutionary phase. And here I'm showing a few examples where binary detailed grid have been used in order to track the, in order to study O and B type stars with black hole binaries, possible ultraluminous X-ray sources with neutron star accretors, or chemically homogeneous evolution from contact binaries. So in POSYDON, POSYDON is a collaboration of around 20 people, mostly astrophysicists, but also computational scientists from the group of Tassos Fragos here in the University of Geneva and from Northwestern University of the group of Vicky Kalogyera. And the idea is to try to develop a tool which keeps much of the flexibility and the computational efficiency of rapid population synthesis codes, but also the accuracy from detailed models. And here, I, of course, need to mention the team of BPAS that have been pursuing this direction several years already. Now, to give an overview of the code, we do not go from birth to of a binary to the formation of compact objects in one binary run, because this would mean that we will lose much of the flexibility that we want, and we will not be able to vary any parameter. We will need to recalculate every time we want to vary something. So what we do is that we use a combination of extensive grids of binary simulations, 3 big grids mainly, which involve 2 hydrogen-rich star or a star and a compact hydrogen-rich star and a compact object, or a helium-rich star and a compact object, and at the same time combine them with on-the-fly calculations of other evolutionary phases, including unstable mass transfer and common envelope evolution, which in reality cannot really be handled during in a stellar code, and the collapse of the stars, and the detached eccentric binary evolution, where we use single stellar models to evolve them. And I will focus to very briefly to each one of them. So firstly, to discuss about our binary detailed grids. For this, we use MESA, which is a state-of-the-art open 1D stellar evolution code that has been invaluable tool for the field of stellar astrophysics and beyond in the last decade. And here I briefly show you the slices of these 3 grids that I have mentioned. On the x-axis in all of them, we have the mass of one star and the initial period of them. And with color, I show you different quantities that we can quite accurately follow. Here, for example, I show the relative angular momentum of the secondary star at the end of the evolution, because this star accreted mass and spun up. On this one, I show you by color the final mass of the neutron star after accreting mass from the stellar component. And on this one, the spin of the helium star just before forming a second compact object. I don't want to go to the details of the binary assumptions that we've made, but I want to stress out that whenever possible, we are taking into account the structure of both of the stars, and we take into account effects like rotation of the 2 stars, tidal interactions. We estimate quite accurately from detailed stellar structure the mass transfer rate, and we have physical motivated mass transfer efficiency. And we can even model contact binaries and chemically homogeneous evolution. For the first version of POSYDON, when it will become public, we are limited for now in grids of solar metallicity. You can understand that this is already quite expensive. We're talking about hundreds of thousands of binary models, but we are already developing grids of other metallicities too. Now, common envelope evolution, which is one of the steps that we calculate on the fly, it's a very important, but also a very uncertain phase of binary evolution. And in general, it has been found that it is very sensitive, like the outcome of it, it's very sensitive to the structure of the envelope of the giant at the onset of common envelope, which is usually parameterized with this lambda parameter. And an advantage here is that we can calculate this lambda at the onset of common envelope in all our binary models, and we don't need to use a fixed value from previous studies. So this improves the accuracy of the outcome of this phase. And for the cases of the collapse of the stars, we are able to evolve our stars up to core carbon exhaustion, which is pretty much a few years before the actual collapse. And this means that we can use the details of the inner structure of the star in order to map it to the explodability parameters, trying to predict whether it will make a neutron star or a black hole, and what will be its probable mass of the compact object. We keep much of the flexibility of the rapid codes, and we are able to use various different supernova prescriptions about the outcome of the collapse. And we have done this in a recent work also for single stellar progenitors there. And we can have a robust estimate of the spin of the compact object after the collapse, because we can take into account the angular momentum of each cell when they collapse, and estimate whether they will end up on the compact object or whether they will form a disk around a possible black hole form, maybe giving rise to a long GRB event. And here I'm putting all these together to show the evolution of one system from birth up to the formation of a of a binary black hole. And I'm showing on the y-axis the period evolution eccentricity, the mass of the two stars, with dust is the second star, and the relative spin of each one of them. And the idea is that we have mass transfer after a few mega years of evolution. We have the collapse of the first star, which makes the orbit eccentric, but tides tend to circularize it. We eventually end up with mass transfer of the secondary star onto the compact object, which lasts only a few thousand years. It goes to unstable common envelope evolution, which shrinks the orbit to less than 1 day. And then we have the evolution of a black hole with a helium star due to winds and tidal evolution. And we end up with two black holes of around 15 and 10 solar masses in this case. And we can even have a pretty good estimate of the spins of this black hole, which is negligible of one and around 0.25 for the other. And after a few giga years, we expect these two binary black holes eventually to merge. Last probably thing to mention is that the way that POSYDON has been written, the infrastructure is modular, which allows for a user to replace, if they want, a binary grid with one that they can calculate with maybe different physics. And in fact, POSYDON gives the tools to run big grids of binary simulation with MESA and post-process them. And at the same time, it can use part of the evolution for part of the evolution of a different code. And we have done this by using Cosmic, which is a rapid population synthesis code for parts of the evolution in preliminary versions of POSYDON up to now, in order to focus on long gamma burst progenitors, black hole progenitors, black hole neutron star progenitors. And to finish, we aspire POSYDON to become a community tool And we are working towards a public release in a few months of the infrastructure, of the instrument paper, of the data, and of the results so far. Thank you very much.
Okay, great. Thank you very much. So there are 3 ways to ask questions. I think 1 is you can speak up, 2 is you can raise your hand, and 3 is you can type your question in the comments, in the chat box. So the floor is open for questions. Okay, yes, Grigoris, go ahead.
Hi, Manos, nice work.
Hi.
I presume that this is quite early, but have you tested the predictions with respect to gravitational wave events so far?
So in preliminary results, we have used, we have tested this in many cases where pretty much the evolution from here up to here is done with rapid population synthesis. And this part has been done more accurately with binary MESA simulations in order to capture the spin of the second black hole. And this has been tested, and there have been various already published results about this. We have not tested yet the case where all of it is based on binary MESA simulations, but pretty much we are doing some early analysis right now for the instrument paper.
Okay, so you're not using BPAS anywhere, right? You're using MESA to do the binary evolution.
Yes.
Okay.
So BPAS is a different code that also uses detailed simulations to evolve the binaries. There are a few differences that in BPAS, only one star is evolved in detail each time, and rotation is not taken into account there. This makes it computationally more efficient, but at the same time, it's more difficult to get more robust estimates about the spins and the inner structure of both components.
Can I ask something as
Yes.
well? Okay, Manos, hello, from
Hello.
Patras. I would like to ask you if you have taken into account the presence of tertiary components that play a very important role in binary systems.
So we have not yet. In most of the cases, in binary population synthesis, the third component is not taken into account. Sometimes the effect of it may be taken into account in the quasi-Lidov effect that may have, that hardens the binaries, but it can be for sure a way towards later versions to take possibly hierarchical triple systems into account.
So with POSYDON, I will have the opportunity to evolve a rotating, tidally interacting binary?
Yes.
Up to merge?
Yes.
Okay. I hope I will see that. Okay.
We have time for one more question, and that's from John Antoniadis. Go ahead.
Can you hear me, Manos? So,
yes.
So great stuff, first of all. I have a slightly more technical question. So in this slide, you show MESA models, MESA binary models that contain compact star and the helium star.
Yes.
So the last part. So my technical question is, so how do you treat the envelope in these models? Because I suspect some of them inflate quite a lot and crash at some point before they reach the carbon burning phase.
So we are using MLT++ in MESA. I think you're familiar with it, which means that this suppresses extreme inflations of the envelope. We still can take into account in cases that we have mass transfer towards the compact object or change the radius because of tidal interactions of these two components. Was this clear? Is there something more specific?
Yes, thanks. I think you should talk with David, who's talking after you at some point. That would be great.
Yeah.
Yeah. Thanks a lot. Great stuff.
Thank you.